Imagine something so dense that a single teaspoon of it would weigh more than a mountain. A sphere no wider than a city, yet containing more mass than our entire sun. A cosmic lighthouse spinning 1,000 times per second, its magnetic field so powerful it could erase your credit cards from halfway across the solar system. These objects exist. They are not science fiction. They are neutron stars, and tonight we journey together to understand what might be the strangest, most extreme physics in the entire universe. Are you ready to have your sense of reality gently unraveled? Let us begin our journey by asking a simple question. What is the densest thing you have ever held in your hand? Perhaps a piece of lead, heavy and cold, or maybe gold, compact and valuable. The densest naturally occurring element on Earth is osmium, and a cube of it the size of a sugar cube would weigh about as much as a brick. But what if we could take matter and compress it further? What if we could squeeze it so tightly that atoms themselves begin to collapse? What would we find at the absolute limit of density, where the rules of everyday physics no longer apply? Neutron stars represent the answer to that question, and it is an answer that defies our everyday intuition. These are objects where gravity has won its ultimate victory over matter, crushing the very structure of atoms into something entirely new. To understand what a neutron star truly is, we must first understand what it is not. It is not a planet. It is not a normal star. It is not even a black hole, though it dances on the edge of becoming one. A neutron star is a cosmic paradox, a city-sized sphere that contains the mass of an entire sun, and we are about to explore every facet of its impossible existence. The story of every neutron star begins not with creation, but with death. Somewhere in the galaxy, a massive star has reached the end of its life. For millions of years, it has fought against the relentless pull of its own gravity, burning fuel in its core to generate the outward pressure needed to keep from collapsing. Hydrogen fuses into helium into carbon and oxygen. The star climbs the periodic table, forging heavier and heavier elements. There is a limit. There is one element that marks the beginning of the end, and that element is iron. Iron is the most stable element in the universe. Using iron into heavier elements does not release energy. Instead, it consumes energy. For a star, this is a death sentence. When the core becomes iron, the nuclear furnace sputters and dies. The outward pressure supporting the star against its own gravity vanishes in an instant. And what happens when you remove the one force holding up something unimaginably massive? It falls. The core collapses inward at nearly a quarter of the speed of light, and in less than a second, the entire inner structure of the star implodes. This is not a gentle process. This is the most violent event in the universe, second only to the Big Bang itself. In that fraction of a second, the core of the star, an object perhaps the size of Earth, collapses down to a sphere only 20 kilometers across. 20 kilometers. That is roughly the size of a large city. Imagine taking our entire planet, with all its mountains and oceans and teeming life, and crushing it down until it could fit within the boundaries of Manhattan. And then keep crushing. The density we are talking about is so extreme that words begin to lose their meaning. We are no longer in the realm of familiar matter. We are entering a place where quantum mechanics and general relativity collide in a dance of cosmic extremes. But the collapse does not stop there, not immediately. The matter of the core is squeezed so tightly that electrons are forced into atomic nuclei, merging with protons to form neutrons. This is called neutronization, and it represents a fundamental change in the nature of matter itself. The star is no longer made of atoms. It is now made almost entirely of neutrons, packed together so closely that they touch. The entire core becomes, in essence, a single giant atomic nucleus, but one that is kilometers wide. We have crossed a threshold into territory that feels more like science fiction than science fact. Yet this is the universe we inhabit. And so, a neutron star is born. But the story of its birth is inseparable from the story of the explosion that announces it to the universe. Because as the core collapses, the outer layers of the star, still falling inward, encounter the incredibly dense core and rebound. They bounce. This rebound generates a shockwave of unimaginable power that tears through the rest of the star, blasting the outer layers into space at a significant fraction of the speed of light. We call this event a supernova, and for a brief moment, it can outshine an entire galaxy. Every heavy element in your body, every atom of gold, silver, and uranium on Earth was forged in this cosmic crucible. In the aftermath of this explosion, the neutron star remains. It sits at the center of an expanding cloud of debris, glowing hot from the energy of its formation, spinning rapidly from the conservation of angular momentum. What was once a star hundreds of thousands of kilometers across is now a pinpoint of matter, a cosmic ember that has passed through the fire of creation and emerged transformed. This is the object we have come to understand, the possible sphere. This monument to the power of gravity and the resilience of matter under the most extreme conditions imaginable. And now we will explore it in detail, layer by layer, property by property, until we can truly grasp what a neutron star is. To truly appreciate a neutron star, we must grapple with the concept of density. Density is simply mass divided by volume. The more mass you pack into a given space, the denser it becomes. Water is denser than air. Rock is denser than water. Lead is denser than rock. But these are all variations on a familiar theme. The atoms themselves are mostly empty space, with tiny electrons orbiting a nucleus that is tens of thousands of times smaller than the atom as a whole. Neutron star eliminates that empty space. It is matter packed so tightly that the empty space is gone and the neutrons themselves are pressed up against one another. How dense are we talking? Imagine taking Mount Everest, the tallest mountain on Earth, and compressing it down to the size of a grain of sand. That is roughly the density of a neutron star. Or consider this. A single teaspoon of neutron star material, about 5 milliliters, would weigh approximately 1 billion tons. 1 billion tons. That is more than the weight of all the cars, trucks, and buses on Earth combined, compressed into a volume you could hold in your hand. If you could somehow bring a teaspoon of this material to Earth, it would instantly plunge through the planet, tunneling down to the core with nothing able to stop it. This density is not just a curiosity. It has profound consequences for everything around the neutron star. Gravity, at its most fundamental level, is a function of mass and distance. The more mass you have, and the closer you are to it, the stronger the gravitational pull. Neutron star packs an enormous mass into an incredibly small space. The result is a gravitational field so strong that it warps the very fabric of space-time itself. Light bends around a neutron star. Time flows differently near its surface than it does in the space far away from it. We are no longer talking about simple Newtonian physics. We are in the domain of Einstein's general relativity. If you could stand on the surface of a neutron star, which you absolutely could not do and survive, you would experience gravity about 100 billion times stronger than what you feel on Earth. You would be instantly flattened into a layer of atoms less than a millimeter thick. Anything falling onto a neutron star accelerates to a significant fraction of the speed of light before it hits the surface. When it impacts, the energy released is so great that the matter is instantly converted into pure radiation. This is not a place where the laws of physics are broken. It is a place where they are pushed to their absolute limits, and we, from our comfortable distance, can only watch in awe. The surface of a neutron star is not smooth. It has a crust, a solid outer layer that is about a kilometer thick. This crust is made of atomic nuclei and electrons, but it is unlike any crust you have ever encountered. The gravity is so intense that the crust is crystallized into a perfect lattice structure, forming the strongest material in the universe. It is billions of times stronger than steel. Mountains on a neutron star, if they exist at all, would be only a few millimeters tall. The gravity is so strong that it would immediately flatten anything taller. The surface temperature can reach millions of degrees, hot enough to emit X-rays and gamma rays into space. Beneath the crust lies the outer core, and this is where the physics becomes truly strange. Here, the neutrons are packed so tightly that they exist in a state called neutron degenerate matter. This is matter where quantum mechanics, not thermal pressure, provides the resistance to further collapse. The neutrons are forced to occupy different quantum states, and this creates a kind of pressure known as degeneracy pressure that holds the star up against gravity. It is a delicate balance, a cosmic standoff between two fundamental forces. Gravity is trying to crush the star into oblivion. Quantum mechanics is saying, not yet, and then, at the very center of the neutron star, lies the inner core. This is the deepest mystery. We do not know for certain what exists at the absolute center of a neutron star because we have never been able to recreate those conditions in a laboratory. The density and pressure are so extreme that matter may transition into exotic states we have only theorized about. Some scientists believe the core may contain a superfluid of neutrons, a frictionless fluid that flows without any resistance. Others speculate that the neutrons themselves may break down into their constituent quarks, forming what is called quark matter. This is the frontier of physics, where our theories are tested at the very edge of their applicability. A neutron star is not just dense. It is a laboratory for physics that we can barely comprehend. It is a place where gravity is so strong that it bends light, where matter exists in states we have never directly observed, where the laws of quantum mechanics and general relativity must work together to describe reality. It is a testament to the power of the universe to create extremes, to push matter and energy to their limits and beyond. And yet, despite all this strangeness, neutron stars are stable. They exist. They are real objects scattered throughout the galaxy, each one a monument to the physics of the impossible. Now that we understand what a neutron star is, let us turn our attention to what a neutron star does. Because these objects are not static. They are not silent. They are, in fact, among the most dynamic and observable objects in the universe, and they owe this visibility to two key properties: rotation and magnetic fields. When the core of a massive star collapses to form a neutron star, the conservation of angular momentum causes the newly formed object to spin incredibly fast. Think of an ice skater pulling in their arms to spin faster. The same principle applies here, but on a cosmic scale, and the results are breathtaking. A typical neutron star can spin hundreds of times per second. Some of the fastest known neutron stars rotate over 700 times per second. 700 rotations in the time it takes you to blink once. At these speeds, the surface of the neutron star is moving at a significant fraction of the speed of light. Points on the equator are traveling at around 20% of light speed. And remember, this is an object with the mass of the sun compressed into a sphere the size of a city. The amount of energy stored in this rotation is staggering, beyond anything we can easily imagine. But rotation alone does not make a neutron star visible. The second key ingredient is the magnetic field. Neutron stars have the strongest magnetic fields in the universe, trillions of times stronger than the magnetic field of Earth. These fields are so powerful that they can tear atoms apart and twist the very structure of space around them. The exact mechanism by which these fields are generated and maintained is still an area of active research, but it is believed to be related to the rapid rotation of the neutron star and the presence of charged particles in and around its crust. These magnetic fields are not aligned with the axis of rotation. Instead, they are often tilted at an angle, like the Earth's magnetic field is tilted relative to our rotational axis. As the neutron star spins, the magnetic poles sweep around, and particles caught in the magnetic field are accelerated to near light speed. These particles emit beams of radiation, primarily in the form of radio waves, X-rays, and gamma rays. These beams shoot out from the magnetic poles, and if one of these beams happens to point towards Earth, we see a pulse of light. A flash. And then darkness. And then another flash. Aww. This is a pulsar. The term pulsar is short for pulsating star, though we now know they are not actually pulsating at all. They are rotating. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student working with astronomer Anthony Hewish. She noticed a strange repeating signal in her radio telescope data. The signal was incredibly regular, pulsing every 1.3 seconds. At first, she and her colleagues were so baffled by the regularity that they jokingly called it LGM-1 for little green men. But as more of these objects were discovered, it became clear that this was a natural phenomenon and an incredibly important one. Pulsars are extraordinarily precise timekeepers. Some pulsars are so regular that they rival the best atomic clocks we have built on Earth. The pulse rate is determined by the rotation rate of the neutron star, and because these objects are so massive and so compact, their rotation is incredibly stable. Over time, pulsars do slow down very gradually as they lose rotational energy through the emission of radiation, but this slowdown is predictable and measurable. This precision has made pulsars incredibly useful tools for astronomers. They can be used to test theories of gravity, to study the interstellar medium, and even to search for gravitational waves. There are thousands of known pulsars in our galaxy, each one a unique cosmic lighthouse. They come in different varieties. There are young pulsars only a few thousand years old, spinning rapidly and emitting powerful beams of radiation. There are old pulsars, millions of years old, spinning more slowly and fading into obscurity. There are millisecond pulsars, which have been spun up to incredible speeds through the accretion of matter from a companion star. And there are magnetars, neutron stars with magnetic fields so strong that they defy comprehension, a subject we will return to later. Each type tells us something different about the life cycles of stars and the extreme physics of the universe. When you look up at the night sky, you cannot see pulsars with your naked eye. They are too small, too distant, and their light is emitted in wavelengths our eyes cannot detect. But they are there, thousands of them, scattered throughout the galaxy, each one spinning silently in the darkness, each one a beacon of impossibly dense matter and unimaginably powerful magnetic fields. And with our radio telescopes, we can hear their whispers, the rhythmic pulses that tell us we are not alone in our curiosity about the universe. We are observers of wonders, and the pulsars are among the most wondrous of all. Among the family of neutron stars, there exists a subclass so extreme, so powerful, that they deserve their own chapter in our journey. These are the magnetars. The name itself evokes their defining characteristic. These are neutron stars with magnetic fields that are not just strong, but stupendously, almost incomprehensibly strong. A typical neutron star might have a magnetic field 1 trillion times stronger than Earth's. Magnetar's magnetic field can be 1,000 times stronger than that. We are talking about magnetic fields in excess of 10 to the power of 15 Gauss. To put this in perspective, The strongest magnetic fields we can create on Earth in specialized laboratories are a few million Gauss. Magnetar's field is billions of times more powerful. How strong is a magnetar's magnetic field? If you were somehow able to approach within 1,000 kilometers of a magnetar and you had any iron in your body, the magnetic field would literally rip the iron atoms from your molecules. The field is so strong that it warps the very atoms that make up matter, distorting their electron clouds into elongated shapes. It can also affect the vacuum of space itself, creating bizarre quantum effects where pairs of particles spontaneously appear and disappear. This is not science fiction. This is the real, observable universe we inhabit, and it is stranger than we ever imagined. Magnetars are rare. We have only identified a few dozen of them in our galaxy. They are thought to form when a particularly massive star collapses, or when the conditions during the supernova explosion are just right to amplify the magnetic field to these extreme levels. Young magnetars are particularly active. Their powerful magnetic fields are in a state of constant flux, twisting and reconnecting, and these processes release tremendous amounts of energy. A magnetar can suddenly brighten, emitting more energy in a fraction of a second than our sun emits in an entire year. These events are called magnetar flares, and they are some of the most energetic events we observe in the universe. One of the most famous magnetar flares occurred on December 27, 2004. A magnetar known as SGR 1806-20, located about 50,000 light-years away from Earth, experienced a massive starquake. The crust of the neutron star cracked under the stress of its own magnetic field, and the sudden release of energy generated a burst of gamma rays so powerful that it reached Earth and measurably affected our planet's ionosphere. For a brief moment, this object, halfway across the galaxy, had a noticeable impact on the protective layers of our atmosphere. It was a humbling reminder of the scale and power of cosmic events. The magnetic fields of magnetars are so strong that they dominate the behavior of the star. The rotation rates of magnetars are generally slower than typical pulsars because the magnetic field acts as a brake, sapping rotational energy. The fields can also cause the crust of the magnetar to crack and shift, leading to starquakes and sudden changes in the rotation rate. These glitches, as they are called, are sudden and unpredictable, and they give us a window into the internal structure of the neutron star. Each glitch tells a story of immense stresses and sudden releases, of a battle between the rigidity of the crust and the power of the magnetic field. As magnetars age, their magnetic fields gradually decay. Over millions of years, the field weakens and the magnetar becomes less active. Eventually, it may fade into a more typical neutron star, or even become a dim, cooling white dwarf of a neutron star, no longer emitting detectable radiation. But during their youth, magnetars are among the most spectacular objects in the cosmos. They are proof that the universe can create magnetic fields of almost unimaginable strength, and they challenge our understanding of how such fields can be generated and sustained. Studying magnetars helps us understand the limits of magnetic fields in the universe. It also provides insights into fundamental physics. The behavior of matter in such extreme magnetic environments can tell us about the properties of quantum electrodynamics, the theory that describes how light and matter interact at the quantum level. Magnetars are natural laboratories where the laws of physics are tested in ways we could never replicate on Earth. They are extreme, they are powerful, and they are utterly fascinating. And they remind us that the universe is full of wonders we are only beginning to comprehend. Neutron stars do not always exist in isolation. Many of them are found in binary systems, orbiting another star or even another neutron star. These binary systems are cosmic laboratories where gravity, radiation, and matter interact in complex and often spectacular ways. When a neutron star has a companion star, the intense gravity of the neutron star can pull matter away from the companion, a process known as accretion. This stolen material spirals down onto the neutron star, forming an accretion disk, and as it does, it releases tremendous amounts of energy in the form of X-rays. These are some of the brightest X-ray sources in the sky. The process of accretion can also spin up a neutron star. If a neutron star is accreting matter from a companion, the infalling material carries angular momentum, and this can cause the neutron star to rotate faster and faster. Over millions of years, an old, slowly rotating neutron star can be spun up to millisecond periods, becoming what astronomers call a recycled pulsar or a millisecond pulsar. These objects are among the fastest rotating objects in the universe, spinning hundreds of times per second, rejuvenated by the stolen mass and angular momentum from their companions. It is a cosmic dance of gravity and matter, and it results in some of the most precisely timed objects we have ever observed. Sometimes, the companion star in a binary system is also a massive star, and when that star reaches the end of its life, it too can explode as a supernova, potentially forming a second neutron star. The result is a binary neutron star system, two incredibly dense objects locked in a tight orbital embrace. These systems are extraordinarily rare, but they are also extraordinarily important. As the two neutron stars orbit each other, they emit gravitational waves, ripples in the fabric of space-time itself. These waves carry energy away from the system, causing the orbit to gradually shrink. Over millions or billions of years, the two neutron stars spiral closer and closer together until, eventually, they collide. The collision of two neutron stars is one of the most violent and energetic events in the universe. When they finally merge, the impact releases more energy in a fraction of a second than the Sun will emit over its entire 10 billion year lifetime. The collision generates a kilonova, a burst of light powered by the radioactive decay of newly formed heavy elements. It also produces a tremendous burst of gravitational waves, powerful enough to be detected by observatories here on Earth. And if the combined mass of the two neutron stars exceeds a certain threshold, the result may not be another neutron star, but a black hole. We witness the creation of a new monster in the cosmic zoo. The first detection of gravitational waves from a neutron star merger occurred on August 17th, 2017. The event, designated GW170817, was observed by the LIGO and Virgo gravitational wave detectors, and within seconds, telescopes around the world turned to observe the event in visible light, X-rays, and gamma rays. It was the first time humanity had observed a cosmic event using both gravitational waves and electromagnetic radiation, a new era of multi-messenger astronomy. The observations confirmed that neutron star mergers are indeed the source of many of the heavy elements in the universe, including gold, platinum, and uranium. The gold in your jewelry, the platinum in catalytic converters, all of it was likely forged in the collision of neutron stars. Binary neutron star systems are also natural laboratories for testing Einstein's theory of general relativity. The gravitational waves emitted by these systems carry information about the masses, spins, and even the internal structure of the neutron stars. By studying these waves, we can learn about the equation of state of neutron star matter, which tells us how matter behaves under the most extreme conditions. We can test whether general relativity holds true in the strong field regime, where gravity is most powerful. And so far, every observation has confirmed Einstein's theory to remarkable precision. The universe, it seems, plays by the rules he discovered. Not all binary systems involve two neutron stars. Sometimes, a neutron star orbits a black hole, and these systems are equally fascinating. The neutron star can orbit the black hole for millions of years, each object tugging on the other with immense gravitational force. Eventually, the black hole may devour the neutron star, tearing it apart through tidal forces before it crosses the event horizon. Or, the two objects may merge, creating a more massive black hole. These events also produce gravitational waves, and they provide us with yet another window into the workings of gravity and the behavior of matter in extreme environments. Binary systems remind us that the universe is not a static place. It is dynamic, ever-changing, with objects in constant motion, interacting with each other in complex and beautiful ways. Neutron stars in binary systems are not solitary wanderers. They are dancers, partners in a cosmic ballet choreographed by gravity. And through our telescopes, both traditional and gravitational wave detectors, we have front-row seats to this performance. We are privileged observers of the universe's most spectacular shows, and binary neutron star systems are among the most captivating acts we have ever witnessed. We have spoken of the immense density and incredible magnetic fields of neutron stars, but there is another aspect of these objects that reveals their dynamic nature. Neutron stars are not perfectly stable. They experience sudden, violent events called starquakes. These are not earthquakes. They are far more powerful. A starquake is a sudden fracture in the solid crust of the neutron star caused by the immense stresses placed on the crust by the star's rotation, magnetic field, or cooling. When the crust cracks, it releases energy and can cause the star to suddenly change its shape or rotation rate. These events are among the most dramatic phenomena we observe in neutron stars. The crust of a neutron star, as we mentioned earlier, is the strongest material in the universe, billions of times stronger than steel. But even the strongest material has limits. As the neutron star ages and cools, its crust contracts. As it rotates and its shape changes slightly due to centrifugal forces, stresses build up in the crust. And when those stresses exceed the strength of the material, the crust fractures. The fracture can be kilometers long, and it releases energy equivalent to millions of powerful earthquakes happening simultaneously. From our perspective, billions of kilometers away, we see a sudden burst of radiation and a change in the pulsar's timing. One of the most observable consequences of a starquake is something called a glitch. A glitch is a sudden, abrupt increase in the rotation rate of a pulsar. Remember, pulsars are slowing down over time as they lose rotational energy. But occasionally, a pulsar will suddenly speed up, spinning faster than it was just moments before. This seems counterintuitive, but the explanation lies in the internal structure of the neutron star. The crust and the interior do not rotate at exactly the same rate. The interior, which may be a superfluid, can rotate faster than the crust. When a starquake occurs and the crust suddenly rearranges itself, it can couple more efficiently to the faster rotating interior, causing the crust to speed up. Glitches have been observed in many pulsars, and they provide valuable information about the internal structure of neutron stars. By studying the size and frequency of glitches, astronomers can infer the properties of the superfluid interior and the coupling between the crust and the core. Some pulsars glitch frequently, while others have only been observed to glitch once or twice. The famous Vela pulsar, one of the brightest pulsars in the sky, experiences a large glitch roughly every 3 years. Each glitch is slightly different, telling a unique story about the internal dynamics of this extraordinary object. Starquakes can also be triggered by the magnetic fields of magnetars. As we discussed earlier, the magnetic fields of magnetars are so strong that they can stress and crack the crust. When the magnetic field suddenly reconfigures itself, it can cause the crust to fracture, releasing a burst of energy that we observe as a magnetar flare. These flares can be incredibly powerful, and they give us a direct view of the interplay between magnetic fields and crustal dynamics. The magnetar is, in a sense, constantly battling against its own magnetic field, and starquakes are one manifestation of this battle. The study of starquakes and glitches is an ongoing area of research. Astronomers monitor pulsars with high precision, looking for these sudden changes in rotation rate. Each glitch provides a new data point, a new piece of the puzzle. Over time, we are building a more complete picture of what happens inside a neutron star and how these incredible objects evolve over time. It is a reminder that even the most extreme, most alien objects in the universe are not static. They are dynamic, changing, and full of surprises. And with each new observation, we learn a little bit more about the nature of matter under the most extreme conditions. Starquakes are a reminder of the immense forces at play within a neutron star. The crust, despite being the strongest material in the universe, is under such tremendous stress that it can fracture, releasing energy on a scale that dwarfs anything we experience on Earth. And yet, the neutron star endures. It continues to spin, to emit radiation, to exist as a testament to the resilience of matter and the power of the laws of physics. In the grand cosmic story, starquakes are but a small chapter, but they are a fascinating one, revealing the hidden dynamics of these stellar remnants. Let us now turn our attention to a different kind of observation, one that does not involve light at all. For most of human history, astronomy has been a visual science. We looked at the sky with our eyes and later with telescopes, capturing the light emitted by distant objects. But light is not the only way the universe communicates with us. There is another messenger, one that travels through the very fabric of space and time itself. Gravitational waves. These are ripples in space-time, generated by the most violent and energetic events in the cosmos. And neutron stars, through their collisions and their rapid orbits, are among the most prolific sources of these waves. Albert Einstein predicted the existence of gravitational waves in 1916 as a consequence of his general theory of relativity. According to the theory, massive objects curve space-time, and accelerating masses create ripples in that curvature that propagate outward at the speed of light. But Einstein himself was skeptical that these waves could ever be detected. They are incredibly weak by the time they reach Earth, causing changes in distance so small that they are measured in fractions of the width of an atomic nucleus. It seemed impossible that we could ever build an instrument sensitive enough to detect them. But we did, the laser interferometer. The signal came from the merger of two black holes over 1 billion light-years away. The waves traveled across the universe for over 1 billion years, and when they finally reached Earth, they stretched and squeezed space by an amount smaller than 1,000th of the width of a proton. LIGO detected them. It was one of the most significant scientific achievements of the century, confirming Einstein's prediction and opening a new window into the universe. And soon after, LIGO and its partner observatory, Virgo, detected gravitational waves from the collision of two neutron stars. The gravitational wave signal from a neutron star merger, designated GW170817, was unlike anything observed before. It lasted for about 100 seconds, a cosmic symphony of two dense objects spiraling closer and closer together, their orbital frequency increasing as they approached the final merger. Astronomers converted the gravitational wave data into sound, a process called sonification, and when you listen to it, you hear a chirp. a rising tone that increases in pitch and volume as the two neutron stars accelerate toward each other, culminating in a final, dramatic crescendo at the moment of collision. It is the sound of space-time itself being shaken by an unimaginably violent event. The detection of gravitational waves from neutron star mergers has given us information we could never obtain through electromagnetic observations alone. By analyzing the gravitational wave signal, we can determine the masses of the neutron stars, their spins, and even place constraints on the equation of state of neutron star matter. This tells us about the fundamental properties of matter at densities beyond anything we can recreate on Earth. It is a form of cosmic archaeology, using the ripples in space-time to learn about the interior structure of objects we can never visit or directly sample. The era of gravitational wave astronomy is still in its infancy. LIGO and Virgo are being upgraded to become even more sensitive. New detectors are being built in other parts of the world, including Japan and India. And there are plans for space-based gravitational wave detectors, such as LISA, the Laser Interferometer Space Antenna, which will be able to detect gravitational waves from even more massive and distant sources. With each new detector, we increase our ability to listen to the universe in this new way, to hear the cosmic events that were once silent to us. We are learning to hear the universe as well as see it. Gravitational waves carry information about the universe that cannot be conveyed by light. They can pass through matter unimpeded, so they allow us to see events that are obscured by dust or gas. They encode information about the most extreme gravitational fields in the universe, places where Einstein's theory is tested to its limits. And they provide a new way to study neutron stars, black holes, and the fundamental nature of space-time itself. We are no longer passive observers of the cosmos, limited to the light that reaches our eyes. We are active listeners, tuning in to the symphony of the universe, hearing the gravitational hum of creation. The detection of gravitational waves from neutron stars is a triumph of human ingenuity and persistence. It took a century from Einstein's prediction to the first detection. It required the construction of some of the most sensitive instruments ever built. It demanded the collaboration of thousands of scientists from around the world. But we did it. We heard the universe speak in a language we had never heard before. And in that sound, in that chirp of colliding neutron stars, we found confirmation of our theories, new knowledge about the nature of matter, and a profound sense of wonder at the universe we are privileged to explore. We have explored the birth of neutron stars in the fiery deaths of massive suns. We have examined their properties, their rotations, their magnetic fields, their collisions. But what is the ultimate fate of a neutron star? Do they exist forever, spinning in the darkness, or do they too eventually meet an end? The answer, as with most things in the universe, depends on the circumstances. A solitary neutron star, isolated in space with no companion to interact with, will slowly cool and fade over trillions of years. It will lose its rotational energy, slowing down until it is no longer emitting detectable radiation. It will become a cold, dark remnant, a black dwarf of a neutron star, invisible to our instruments. But the universe is a dynamic place, and isolated neutron stars are relatively rare. Many neutron stars are part of binary systems, and the presence of a companion star can dramatically alter their fate. If the companion is another massive star, it may eventually undergo a supernova and form a second neutron star, leading to a binary neutron star system. These systems, as we have discussed, will eventually merge due to the emission of gravitational waves. The merger can result in a more massive neutron star, a hypermassive neutron star that is temporarily supported against collapse by its rapid rotation. Or, if the combined mass exceeds a critical threshold, the merger can produce a black hole. The maximum mass a neutron star can have is known as the Tolman-Oppenheimer Volkoff limit, named after the physicists who first calculated it. This limit is somewhere between about 2 and 3 solar masses, depending on the equation of state of neutron star matter, which we still do not know precisely. If a neutron star exceeds this mass, the degeneracy pressure of the neutrons is no longer sufficient to resist gravity. The star collapses, and the only thing that can stop it is nothing. It collapses into a singularity, a point of infinite density surrounded by an event horizon. Like becomes a black hole. The neutron star has met its ultimate fate, transformed into the most enigmatic object in the universe. Not all neutron star mergers result in immediate black hole formation. If the combined mass is close to, but not quite above, the Tolman-Oppenheimer. Volkoff limit, the result may be a hypermassive neutron star. This object is temporarily supported by its rapid rotation, which generates centrifugal forces that help resist gravity. But this is only a temporary reprieve. As the hypermassive neutron star loses rotational energy through the emission of gravitational waves and electromagnetic radiation, it slows down. Eventually, the rotation can no longer support it and it collapses into a black hole. This process can take seconds, minutes, or even hours, providing a brief but fascinating window into the final moments of a neutron star's life. There is also the possibility that a neutron star could accrete enough matter from a companion star to push it over the mass limit. In a binary system where a neutron star is pulling matter from a giant star, the neutron star's mass increases over time. If it accretes enough material, it could exceed the Tolman-Oppenheimer. This is a slow process, taking millions of years, but it represents another pathway by which neutron stars can end their existence. The universe is patient, and it has many ways to transform one type of object into another. Some neutron stars may meet an even more exotic fate. There are theoretical predictions that, under certain conditions, the matter in the core of a neutron star could undergo a phase transition, converting into strange quark matter. This hypothetical form of matter consists of up, down, and strange quarks in roughly equal numbers. If this transition occurs, the neutron star could become a strange star or a quark star, an object with properties intermediate between a neutron star and a black hole. This is highly speculative, and we have no confirmed observations of such objects. But the universe is full of surprises, and it is possible that some of the objects we call neutron stars are actually something else entirely. The ultimate fate of a neutron star, then, is varied. It depends on whether it is isolated or in a binary system, whether it can accrete matter, whether it merges with another neutron star or black hole. But in all cases, the neutron star represents a waypoint in the life cycle of matter in the universe. Matter begins in the Big Bang, coalesces into stars, is forged into heavier elements through nuclear fusion, and is scattered through space in supernova explosions. Some of that matter becomes compressed into neutron stars, the densest stable form of matter we know. And some of those neutron stars eventually collapse into black holes, the densest objects of all. It is a cycle of creation, destruction, and transformation that has been ongoing for billions of years. Neutron stars are not eternal, but they are incredibly long-lived on human timescales. A solitary neutron star could, in principle, exist for trillions of years, long after all the stars in the universe have burned out and the cosmos has entered its final, dark era. They are among the most resilient objects in the universe, stubborn relics of stellar death that refuse to disappear quietly. And even when they do finally meet their end, whether through collapse into a black hole or by fading into darkness, they leave behind a legacy. They enrich the universe with heavy elements. They generate gravitational waves that we can detect billions of years later. They teach us about the nature of matter, gravity, and space-time. They are, in the truest sense, cosmic monuments. Throughout this journey, we have explored neutron stars from many angles: their formation, their properties, their behaviors, their fates. But there is a deeper question we must ask. What do neutron stars tell us about the universe itself, about the fundamental nature of reality? Neutron stars are not just interesting astronomical objects. They are laboratories where the laws of physics are tested under the most extreme conditions. They are places where quantum mechanics and general relativity, the two pillars of modern physics, meet and interact. And by studying them, we gain insights into the very fabric of space-time, the nature of matter, and the limits of our understanding. General relativity tells us that mass and energy curve space-time, and that this curvature is what we experience as gravity. Neutron stars, with their immense mass packed into a tiny volume, create some of the strongest gravitational fields in the universe. Near a neutron star, space-time is so severely curved that time itself flows differently. A clock on the surface of a neutron star would tick measurably slower than a clock in interstellar space. Light emitted from the surface is redshifted, its wavelength stretched by the gravitational field. And the path of light is bent so much that you could, in principle, see around the star, observing the far side by looking at light that has been bent by gravity. Quantum mechanics, on the other hand, governs the behavior of matter at the smallest scales. In the interior of a neutron star, quantum mechanics is crucial. The neutrons are packed so tightly that they are governed by the Pauli exclusion principle, a quantum mechanical rule that says no two identical fermions can occupy the same quantum state. This creates degeneracy pressure, the force that supports the neutron star against gravity. Without quantum mechanics, the neutron star would collapse instantly. So here we have an object where quantum mechanics, which usually governs the realm of atoms and subatomic particles, plays a role on cosmic scales. It is a beautiful marriage of the very small and the very large. One of the greatest challenges in modern physics is reconciling general relativity and quantum mechanics into a single, unified theory. These two theories are incredibly successful in their respective domains, but they are fundamentally incompatible at a deep level. General relativity treats spacetime as smooth and continuous, while quantum mechanics suggests that spacetime may be discrete and granular at the smallest scales composed of quanta of space and time. Neutron stars, and especially their more extreme cousins, black holes, are places where both theories must apply, and where the contradictions between them become most apparent. By studying neutron stars, we are probing the boundary between these two great theories, searching for clues that might lead us to a theory of quantum gravity. Neutron stars also allow us to explore the equation of state of matter. The equation of state is a mathematical relationship that describes how matter behaves under different conditions of pressure, temperature, and density. For everyday matter, we understand the equation of state quite well. But for matter at the densities found in neutron star cores, we are much less certain. Different theoretical models of nuclear interactions predict different equations of state, and these different equations of state lead to different predictions for the size, mass, and behavior of neutron stars. By observing neutron stars, measuring their masses and radii, and detecting gravitational waves from their collisions, we can test these theoretical models and narrow down the possibilities. The discovery of gravitational waves has added a powerful new tool to our arsenal. Gravitational waves from neutron star mergers carry information about the tidal deformability of the neutron stars, which is a measure of how easily they are distorted by the gravitational pull of their companion. This tidal deformability depends directly on the equation of state. By measuring it, we can learn about the internal structure of neutron stars and the properties of matter at nuclear densities. This is information we cannot obtain in any other way. We cannot build a laboratory on Earth that can recreate the conditions inside a neutron star, but the universe has built countless such laboratories, and it has given us the tools to study them. Beyond their role in testing fundamental physics, neutron stars also play a crucial role in the chemical evolution of the universe. As we have discussed, neutron star mergers are believed to be the primary source of many of the heaviest elements in the periodic table, including gold, platinum, and uranium. These elements cannot be produced in ordinary stellar nucleosynthesis. They require the extreme conditions of a neutron star merger, where the rapid neutron capture process, known as the R process, can forge these heavy nuclei. Every atom of gold in your jewelry, every bit of uranium in nuclear reactors, was likely created in the collision of two neutron stars billions of years ago. We are, quite literally, made of stardust, and some of that stardust came from neutron stars. Neutron stars are, in many ways, microcosms of the universe itself. They contain within them the history of stellar evolution, the physics of nuclear reactions, the dynamics of gravity, and the mysteries of quantum mechanics. They are bridges between the macroscopic world we inhabit and the quantum world that underlies it. They are monuments to the creative and destructive power of the cosmos. And they are reminders that we live in a universe governed by laws that we can discover, understand, and use to make sense of the incredible diversity and complexity of the world around us. Studying neutron stars is not just about understanding these particular objects. It is about understanding the universe and our place within it. As we near the end of our journey, it is time to reflect on what neutron stars mean to us, not just as scientists or astronomers, but as human beings. It is easy to think of neutron stars as alien, as objects so extreme and so distant that they have no connection to our everyday lives. But that would be a mistake. Neutron stars are intimately connected to our existence. The atoms that make up your body, the iron in your blood, the calcium in your bones, the oxygen you breathe, all of these elements were forged in the nuclear furnaces of stars. And many of the heaviest elements, the gold in your ring, the iodine in your salt, were created in the violent collisions of neutron stars. Carl Sagan famously said that we are made of star stuff, and he was absolutely right. But we can be even more specific. We are made of the ashes of dead stars, the remnants of supernovae, and the debris of neutron star collisions. Every breath you take, every beat of your heart is a testament to the cosmic processes that have been shaping the universe for billions of years. You are not separate from the cosmos. You are a part of it. You are a way for the universe to know itself, to explore itself, to marvel at its own wonders. And neutron stars, in their extreme and alien beauty, are a reminder of just how interconnected everything truly is. Neutron stars also teach us about the nature of limits. They exist at the edge of what is physically possible. They are the densest stable objects in the universe. They have the strongest magnetic fields. They spin at the fastest rates. They push the laws of physics to their breaking point, and by doing so, they reveal the boundaries of those laws. In our own lives, we too encounter limits, physical, mental, emotional. But neutron stars remind us that limits are not walls. They are frontiers. They are places where new understanding begins. By pushing against our limits, by exploring the extremes, we discover new possibilities and expand our understanding of what is real and what is possible. There is also a profound humility in contemplating neutron stars. These objects were formed billions of years ago in explosions so violent they outshone entire galaxies. They have existed for unimaginable spans of time, spinning silently in the darkness, indifferent to our existence. The universe does not care about us. It does not exist for our benefit. And yet, we have the capacity to understand it, to study it, to appreciate its beauty. We are fleeting creatures, our lives brief flashes in the cosmic night. But in that brief flash, we can reach out with our minds and touch the infinite. We can understand neutron stars, objects separated from us by distances and timescales that dwarf human comprehension. That is something remarkable. In a universe that is often chaotic, violent, and indifferent, neutron stars offer a strange kind of comfort. They are governed by laws. They are predictable. We can observe them, measure them, and understand them using the tools of mathematics and physics. In a very real sense, neutron stars are proof that the universe makes sense, that it is not arbitrary, that there are patterns and rules underlying the apparent chaos. And if we can understand neutron stars, then perhaps we can understand anything. Perhaps there is no limit to what the human mind can achieve, given enough time, curiosity, and persistence. Neutron stars also inspire wonder. Wonder is a fundamental human emotion, one that has driven exploration and discovery throughout our history. When we look at a neutron star, when we contemplate its impossible density, its rapid spin, its powerful magnetic fields, we are filled with a sense of awe. How can such a thing exist? How does the universe create such marvels? These questions drive us to learn more, to explore further, to push the boundaries of our knowledge. That sense of wonder, that childlike curiosity about the world, is something we must never lose. It is what makes us human, and it is what will carry us into the future. In studying neutron stars, we are engaging in an activity that is uniquely human. No other species on Earth, as far as we know, contemplates the universe in the way we do. No other species builds telescopes, develops theories, or seeks to understand the nature of reality. This capacity for abstract thought, for scientific inquiry, for cosmic contemplation is one of the things that makes us special. It is a gift, and it carries with it a responsibility. The responsibility to use our knowledge wisely, to preserve the beauty and diversity of our planet, and to ensure that future generations can continue to explore and understand the cosmos. Ultimately, our connection to neutron stars is a connection to the universe itself. We are part of an unbroken chain that stretches back to the Big Bang, through the formation of galaxies and stars, through supernovae and neutron star collisions, to the present moment. We are the universe, looking back at itself, a brief moment of self-awareness in the vast cosmic drama. And in that moment, we have the opportunity to appreciate the beauty, the complexity, and the sheer wonder of existence. Neutron stars are not just objects to be studied. They are invitations to contemplation, to reflection, to a deeper understanding of who we are and where we came from. And for that, we should be grateful. As we conclude our journey through the realm of neutron stars, let us turn our gaze toward the future. What lies ahead in our study of these remarkable objects? What new discoveries await us? The future of neutron star research is bright, filled with promise and potential. New telescopes, both on the ground and in space, are coming online or being planned. The Square Kilometre Array, a massive radio telescope that will span continents, will be able to detect pulsars with unprecedented sensitivity. It will discover thousands of new pulsars, including rare and exotic systems that will test our understanding of physics in new ways. Each new pulsar is a new data point, a new piece of the puzzle. The next generation of X-ray and gamma-ray telescopes will allow us to study the high-energy emission from neutron stars in greater detail. We will be able to map the surface of neutron stars, looking for hotspots where the magnetic field channels matter onto the poles. We will study magnetar flares with high time resolution, capturing the rapid changes in emission that occur during these violent events. And we will search for new types of neutron stars, perhaps discovering objects that do not fit neatly into our current categories. The universe is full of surprises, and we should be prepared to encounter phenomena we have not yet imagined. Gravitational wave astronomy is still in its infancy, and the coming decades will see enormous advances. The sensitivity of LIGO and Virgo will continue to improve, allowing them to detect fainter signals from more distant sources. New detectors will come online, forming a global network that can pinpoint the location of gravitational wave sources with high precision. And eventually, space-based detectors like LISA will open up entirely new frequency ranges, allowing us to detect gravitational waves from supermassive black hole mergers, from the early universe, and from other exotic sources. Each detection is a gift, a new window into the universe that was previously closed to us. One of the most exciting prospects is the possibility of detecting gravitational waves from a single, isolated neutron star. If a neutron star has a mountain on its surface, even a tiny one only a few millimeters tall, the rotation of that mountain will generate gravitational waves. These waves would be incredibly weak, but with sufficiently sensitive detectors, they could be detected. This would give us a direct probe of the crust and internal structure of the neutron star, telling us about the equation of state in a completely independent way. It is a challenging goal, but it is within reach, and it would be a monumental achievement. There is also great interest in using pulsars as tools for detecting gravitational waves at different frequencies. The timing of pulsar pulses is so precise that if a gravitational wave passes between us and the pulsar, it will cause a tiny, measurable change in the arrival time of the pulses. By monitoring an array of pulsars across the sky, we can search for the signature of gravitational waves with periods of years or decades. These waves would be generated by supermassive black hole binaries in the centers of distant galaxies. This technique, known as pulsar timing arrays, is already underway, and there are hints that we may be on the verge of a detection. It would be another triumph for multi-messenger astronomy. Advances in theoretical physics will also play a crucial role. As our computational power increases, we will be able to run more sophisticated simulations of neutron star interiors, supernovae, and neutron star mergers. These simulations will help us interpret observations and make predictions about what we should see. We will develop better models of the equation of state, incorporating the latest results from nuclear physics experiments. And we will continue to wrestle with the deep questions of quantum gravity, seeking a unified theory that can explain both the quantum world and the gravitational world. Neutron stars will be our testing ground, the place where theory and observation meet. Perhaps most exciting is the possibility of discovering something entirely unexpected. The history of astronomy is filled with surprises. Pulsars themselves were a surprise, discovered by accident while searching for something else entirely. Gamma-ray bursts, fast radio bursts, magnetars, all of these phenomena were unknown until we stumbled upon them. As our instruments become more sensitive and our surveys more comprehensive, we are almost certain to discover new types of neutron stars, new behaviors, new physics. The universe has a way of exceeding our expectations, and we should approach the future with open minds and a willingness to be astonished. The future of neutron star research is also a future of collaboration. Modern astronomy is a global enterprise, with scientists from around the world working together to solve the mysteries of the universe. Data is shared freely. Telescopes are operated by international consortia. Discoveries are celebrated collectively. This spirit of collaboration is one of the most hopeful aspects of modern science. It reminds us that despite our differences, we are all part of the same species, sharing the same planet, looking up at the same sky. Neutron stars are not the property of any one nation or group. They belong to all of humanity, and it is together that we will unlock their secrets. As our journey nears its end, let us take one final look at these remarkable objects and the universe they inhabit. Neutron stars are dancers in the cosmic ballet, spinning endlessly in the darkness. They are lighthouses guiding us through the night, their pulses marking time with astonishing precision. They are forges where the heaviest elements are created. They are laboratories where physics is tested at its extremes. They are monuments to the creative and destructive power of the cosmos. And they are, above all, reminders that the universe is far stranger, far more beautiful, and far more wondrous than we ever imagined. Think about what we have learned on this journey. We have seen how massive stars end their lives in spectacular explosions, leaving behind cores compressed to unimaginable densities. We have explored matter in a state that exists nowhere else in the universe. Neutrons packed together so tightly that an entire star becomes, in essence, a single atomic nucleus. We have witnessed the fastest rotations, the strongest magnetic fields, and the most powerful gravitational waves. We have heard the sound of space-time itself being shaken by colliding neutron stars. And we have traced the origins of the elements in our own bodies back to these cosmic events. Neutron stars remind us that the universe operates on scales both vast and tiny, timescales both fleeting and eternal. A neutron star can form in less than a second during a supernova collapse, yet it can exist for trillions of years afterward. It is smaller than a city, yet it contains more mass than our sun. It spins hundreds of times per second, yet its timing is more precise than the best atomic clocks we have built. These paradoxes are not contradictions. They are invitations to expand our thinking, to embrace the counterintuitive nature of reality, to accept that the universe is not required to conform to our everyday experience. There is a kind of poetry in neutron stars. They are born from death, forged in the ashes of destroyed suns. They are both creators and destroyers, enriching the universe with heavy elements while embodying some of the most violent processes known to physics. They are silent yet speaking to us through their pulses and gravitational waves. They are isolated yet connected to everything around them through gravity and the elements they create. They exist at the edge of what is possible, pushing against the boundaries of existence itself. And in doing so, they reveal to us the fundamental nature of the cosmos. When you look up at the night sky tonight, you will not see neutron stars with your naked eye. They are too small, too distant, too faint. But they are there, thousands of them, scattered throughout our galaxy and beyond. Each one is spinning in the darkness, a tiny ember of impossibly dense matter. Each one is a story, a history of stellar birth, life, and death. Each one is a piece of the puzzle we are trying to solve, a clue to understanding the nature of the universe. And now that you know they are there, now that you understand what they are, the night sky will never look quite the same again. Neutron stars teach us that beauty exists in places we least expect it. There is beauty in the elegant mathematics that describes their structure. There is beauty in the precision of their pulses. There is beauty in the way they test our understanding of physics and push us to think more deeply. There is even a kind of terrible beauty in their violence, in the supernova explosions that create them and the collisions that destroy them. This is not the gentle beauty of a sunset or a flower. This is the sublime beauty of nature at its most extreme, most powerful, most uncompromising. And it is no less worthy of our appreciation. As we bring our journey to a close, I want you to carry with you not just facts and figures, but a sense of wonder. Wonder at the fact that such objects can exist. Wonder at the fact that we, tiny creatures on a small planet, can understand them. Wonder at the fact that the atoms in your body were forged in the hearts of stars and the collisions of neutron stars. You are not just an observer of the universe. You are a participant. You are made of the same stuff as neutron stars, governed by the same laws, part of the same cosmic story. And that story is still being written. The universe is vast beyond comprehension, ancient beyond measure, and filled with wonders we are only beginning to discover. Neutron stars are just one chapter in this grand cosmic narrative, but what a chapter it is. From their violent births in supernova explosions to their eventual fates as black holes or cold remnants, they embody the cycles of creation and destruction that have shaped the universe for billions of years. They are proof that reality is stranger than fiction, that the universe is more creative than any human imagination. And they are an invitation to never stop asking questions, never stop seeking answers, never stop marveling at the extraordinary cosmos we are privileged to call home. Thank you for joining me on this journey to the realm of neutron stars. We have explored the densest matter in the universe, witnessed the fastest rotations and strongest magnetic fields, and heard the gravitational symphony of colliding stellar remnants. But this is not an ending. It is an invitation to continue exploring, to keep looking up, to never lose that sense of wonder that makes us human. The universe is waiting, filled with mysteries yet to be solved and wonders yet to be discovered. And perhaps, on some quiet night when you look up at the stars, you will remember the neutron stars spinning silently in the darkness, and you will smile, knowing that you understand just a little bit more about the extraordinary cosmos we inhabit. Until our next journey together, keep wondering, keep questioning, and keep exploring. The universe is yours to discover.